All right, so our last video is over osmolarity, right? So when we're talking about osmosis and those iso, hypo, hypertonic solutions, right, we're actually going to be worried about osmolarity, which is a new thing, but it's related to molarity. So again, all colligative properties depend on the amount of solute that's in the solution. It doesn't really matter what the solute is, it just matters, right, that it's in there, and it depends on how many particles are floating around. So osmolarity is going to involve a new factor, right? I'm going to have this I value that that is going to come into play. And it says I here is the number of ions in a compound that dissociate into that solution. So that's what we're typically going to talk about it for. But if we're not talking about an ionic compound, the value for I is just 1. Because if I have sugar dissolved in water, each sugar molecule contributes to the colligative properties in the solution, right? And it matters how many molecules are dissolved in that water. But if it's an ionic compound, it's a little bit different because there's more than one piece, right? If I have sodium chloride dissolved in solution, right, there are actually two different ions, sodium and chlorine and chloride, that will separate in that solution, right? Those two ions will float freely in that solution, and each one can contribute to the colligative properties, right? Which is different than maybe calcium chloride, right? If I had calcium chloride, excuse me, the pen's being kind of goofy. If I had calcium chloride, there's actually one calcium and two chloride ions floating around. So now my I value is 3 because there's 3 separate things floating around in that solution that can all affect my colligative properties. So that I is something you need to learn how to recognize, right? We'll go through some examples in class so that you can see a lot of them. But essentially, sodium chloride has 2 ions, calcium chloride has 3 ions, right? That's how you'd come up with your I value. Whereas if it was sugar, if it was glucose, C6H12O6, or that dextrose the other day that we used in lab, which is just a form of glucose, right? The value for this one is just 1 because that's just one thing that's floating around in the solution. It doesn't have multiple pieces that separate once you dissolve it in that solution. So I can range in value from 1 to many, but otherwise to use it is you just do problems like this. If I have a molar solution of calcium nitrate, if I have a 0.15 molar solution of calcium nitrate, in order to find out whether it's iso, hyper, or hypotonic, I have to first turn that into an osmolarity. So my equation, right, is this osmolarity times molarity, or excuse me, osmolarity equals molarity times I, right? It'd be a little easier to follow if it looked more like this. Let me switch to black real quick. Osmolarity, this is my symbol for that, is equal to molarity times I. I'll use that as an equation. If I have a 0.15 molar solution of calcium nitrate, again, that's going to be kind of important that you know what this is. Because calcium nitrate, those are my 2 ions, but I also have to know that nitrate has a -1 charge, so I need 2 of those for every calcium. Right, this is what I was talking about when we were memorizing those ions. It's hard to do problems when you don't actually know what the formula looks like, because I need to know what the value for I is for calcium nitrate. And unless I do that correctly, there's no way that I would know that there's 1, 2, 3 ions involved. So I'm going to take that 0.15 times 3, but otherwise it would depend on what I'm doing, right? It would depend on the substance, whether it's calcium nitrate, calcium chloride, sodium hydroxide, whatever it happens to be. All things have unique values for I. But in this case, if I multiply 0.15 times 3, I'm going to get 0.45, right? Osmolar. 3 is a whole number that I don't have to use for sig figs because it's literally 3. You counted 3 ions, right? So it's just 2 sig figs before and after. I don't have to round in this case. But now if I'm trying to compare that 0.45 to 0.3, is it bigger, smaller, the same, right? If it's bigger, then I have a hypertonic solution. Hyper means above, right? Bigger than normal. So I have a hypertonic solution in this case. So that's what a problem might look like. You might also get a problem that looks like this. And this one's a little bit more complicated because I actually have to do some calculations, right? Remember, a 0.9% solution is just mass volume, grams in a certain number of milliliters, and it doesn't have moles in it, right? So I'm going to have to get moles before I can figure out what the molarity of the solution is, before I can figure out the osmolarity of the solution. So this is a multi-step process, right? But it really isn't that difficult. It shouldn't be that tough. So the first thing I have to realize is that I have to use that equation for mass volume. 0.9% is 0.9 over 100, right? Well, if I make my volume, which wasn't specified, of the sodium chloride solution exactly 100, then I already know what the value for x is. It's 0.9, right? Very simple so far. So I could just have 0.9 grams of that salt, this dissolved in 100 milliliters, and it would make a 0.9% solution. That's the first step. Figure out how many grams you have. Second step is to turn grams into moles. So if I'm going to get a molarity, I need moles. And remember, salt is 58.44 grams per mole. But then my next step, once I find out my mole, is I have to figure out a molarity. And molarity is moles per liter. So again, I already had a set amount of volume over here that I decided on. I assumed it would be 100 milliliters, right? So that's equal to 0.1 liters that I can put in my work over here. Now you could just solve for moles and then divide by 0.1 liters, but I like to put it all in one thing, right? Because then the grams go away. Moles divided by liters should give me a molarity. So I just take 0.9 divided by 58.44 and then divide again by 0.1. And I'm going to get an answer of 0.154. I am aware that I'm going to have to round eventually, but I'm not going to do that right away because this is just a molarity. And my next step is to figure out, okay, remember sodium chloride? There's an I value for sodium chloride that I need to worry about. There are 2 ions in here, so I need to double this, right? So I have to do my osmolarity calculation, which finally will get me to an answer of 0.308 osmolar. And again, since I'm comparing to this 0.3 up here, and technically I started with the 0.9, right? I only really get 1 sig fig in this, so I could round that to 0.3 osmolar, which is exactly the same as what I need it to be, right? The concentration inside of my blood cells is 0.3 osmolar. So the concentration outside my blood cells needs to be the same for it to be an isotonic solution. So a 0.9% saline solution is a perfect IV solution. And it's really simple. You can put 0.9 grams of salt in 100 milliliters of water, or those IV bags hold a liter, but 0.9 grams divided by 1,000, just move the decimal, right? That's going to make that perfect isotonic solution that could be used for your IV. So some of you have probably seen that, a 0.9% saline solution on an IV bag. Otherwise, maybe you've never had an IV before, but next time you see one, just check it out. There's one more problem in those practice problems, but we'll do that together in class.